Most people think they know sharks. Great whites, hammerheads, tiger sharks patrolling coastlines and coral reefs. But those familiar predators exist in a world of sunlight and visibility. Descend past the reach of daylight, past where most marine life can survive, and you'll find sharks that seem designed by something with a very different idea of what a predator should look like. These deep-sea sharks don't just look strange. They've evolved in ways that challenge our understanding of what's possible in a living creature. The deeper you go, the more disturbing they become. At around 200 meters below the surface, sunlight begins to fade significantly. This is the edge of what scientists call the twilight zone, where the ocean transitions from the familiar blue waters of the surface to something far more alien. The sharks that live here are the first indication that something fundamentally changes in the deep ocean. They're still recognizable as sharks, but differences start to appear. The big-eye thresher shark lives at these intermediate depths, and its most striking feature is right there in its name. Its eyes are massive, disproportionately large for its body, each one the size of a human fist. These enormous eyes gather every available photon of light in the dimness, allowing the shark to see in conditions that would leave surface sharks functionally blind. The expansion of the eye changes the shark's entire facial structure, giving it an appearance that's unsettling in its exaggeration. But eye size is just the beginning of the adaptations we see at these depths. The cookie cutter shark, which ranges from 300 to 600 meters deep, has developed a feeding strategy unlike anything found in surface waters. This small shark, rarely more than 50 centimeters long, is a parasite of larger animals. It has lips that work like a suction cup, allowing it to attach to whales, dolphins, and large fish. Then it uses its teeth, which are disproportionately large and arranged in a saw-like formation, to cut out a circular plug of flesh from its victim. The cookie cutter's teeth are remarkable in their own right. The lower jaw contains a single row of teeth that are fused together, creating a continuous cutting edge like a hole saw. When the shark bites, it doesn't tear or rip. It cores out a perfect circular chunk of tissue. The wounds left on victims are distinctive, circular craters that look precisely machined. These sharks have attacked submarines, mistaking them for prey, and left perfect circular holes in rubber sonar domes. The bite marks are so clean they look artificial. What makes the cookie cutter particularly unsettling is its bioluminescence. The underside of its body glows with a soft green light, except for a dark collar around its throat. From below, this makes the shark look like a small fish, the dark collar resembling a fish's silhouette against the dim light from above. Larger predators rise to attack what they think is an easy meal, only to have the cookie cutter latch onto them and take its circular bite. The Twilight Zone sharks show us the first major changes that depth creates: enhanced sensory organs, unusual feeding strategies, and the beginning of bioluminescence. But these sharks still maintain a relatively normal shark body plan. They're strange, but they're still clearly sharks. Descend further, and that starts to change. The adaptations become more extreme, the appearances more disturbing, the biology more alien. Below 1,000 meters, the ocean enters what's called the midnight zone. No sunlight penetrates here at all. The pressure is crushing, the temperature hovers just above freezing, and food is scarce. The sharks that survive here have evolved into forms that barely resemble their surface relatives. The goblin shark is perhaps the most famous, and for good reason. It looks like something from a nightmare. The goblin shark's most striking feature is its elongated snout, a blade-like projection that extends far beyond its jaws. This isn't decorative. The snout is packed with electroreceptors called ampullae of Lorenzini, far more densely concentrated than in any surface shark. These organs detect the tiny electrical fields generated by muscle contractions in prey animals. In the complete darkness of the deep ocean, where vision is almost useless, the goblin shark hunts by sensing the bioelectric signatures of living things. But the snout is just the beginning of the goblin shark's strangeness. Its jaws are protrusible, meaning they can extend outward from its skull, like something from an alien movie. When the shark detects prey, its jaws shoot forward, projecting out of its mouth, grab the prey, and then retract. This happens in a fraction of a second. The jaws can extend nearly to the tip of the elongated snout, creating a reach that's impossible for sharks with fixed jaws. The skin of the goblin shark is another disturbing feature. It's soft and flabby compared to the tough hide of surface sharks, with a translucent pink color that comes from blood vessels visible beneath the skin. The texture is described as almost gelatinous. This soft body is an adaptation to the deep ocean, where where the tremendous pressure makes rigid structures less practical. The goblin shark's body compresses under pressure, becoming denser without being crushed. Goblin sharks are rarely seen alive. Most specimens have been caught accidentally by deep-sea fishing operations or found dead after washing ashore, but enough specimens exist to understand that this shark is not rare, just reclusive. It lives at depths between 900 and 1,300 meters normally, though some have been found as deep as 1,600 meters. At these depths, the water pressure is over 160 times what we experience at the surface. The frilled shark shares the goblin shark's habitat and its nightmarish appearance. This shark looks more like an eel than a typical shark, with an elongated body and a head that seems too small for its length. But it's the mouth that truly disturbs people. The frilled shark has 300 teeth arranged in 25 rows, each tooth with 3 sharp prongs. When the mouth is open, these teeth point backward, creating a throat lined with inward-pointing needles. The frilled shark's hunting strategy involves those teeth. It strikes at prey, usually squid, and the backward-pointing teeth make escape impossible. Any struggle just drives the prey further into the shark's mouth. The shark then swallows the prey whole, its flexible jaws and throat allowing it to consume animals nearly as large as itself. Specimens have been found with intact squid in their stomachs, some of them showing signs they were alive when swallowed. The reproduction of frilled sharks is as disturbing as their appearance. They have the longest gestation period of any vertebrate, up to 42 months. A female frilled shark carries her young for 3.5 years before giving birth. During this time, the embryos develop slowly in the cold, food-scarce environment of the deep ocean. When finally born, the pups are large and well-developed, ready to hunt in the darkness immediately. But perhaps the most unsettling aspect of midnight zone sharks is how little we know about them. These sharks have been photographed, caught, and studied, but we've never observed them hunting in their natural habitat. We don't know how often they feed, how they interact with each other, or how they navigate the pitch-black depths they call home. Every specimen tells us something new, and often that new information is deeply disturbing. Below 3,000 meters, we enter the abyssal zone. The pressure here exceeds 300 atmospheres. The temperature is barely above freezing. Food is so scarce that the entire ecosystem functions on a different energy budget than the world above. The sharks that live here have evolved into forms that seem barely alive, yet they're perfectly adapted to their extreme environment. The Portuguese shark and the Pacific sleeper shark both inhabit these abyssal depths. They're large animals, some exceeding 5 meters in length, but they move in slow motion. Their metabolisms run at rates that seem impossibly slow. These sharks can go months between meals, their bodies operating on minimal energy, waiting for the rare opportunities when food appears in their territory. The sleeper sharks get their name from their lethargic appearance. They swim slowly, almost drifting through the water, giving the impression of barely being conscious. But this appearance is deceptive. These sharks are ambush predators, and their slow movement makes them nearly invisible in an environment where most animals use motion detection to find prey. When prey comes close, the sleeper shark accelerates in a sudden burst that contradicts its usual torpor. What makes abyssal sharks truly creepy is their diet. At these depths, food scarcity forces sharks to become extreme opportunists. Sleeper sharks have been found with seal, fish, squid, and carrion in their stomachs, but they've also been found with polar bear remains, reindeer, and even whole seabirds. How a slow-moving deep-sea shark ends up with a polar bear in its stomach remains a mystery. Some scientists believe sleeper sharks may venture into shallower Arctic waters to scavenge, while others suggest they might attack animals swimming at the surface. The teeth of abyssal sharks reflect their opportunistic feeding. The Portuguese shark has small, sharp teeth in its upper jaw and larger, blade-like teeth in its lower jaw. This configuration allows it to both grip and slice, useful for dealing with whatever food sources it encounters. The teeth themselves are constantly replaced, like all sharks, but the rate of replacement in deep-sea sharks is much slower than in surface species. Bioluminescence becomes more important in the abyssal zone. Many sharks at these depths have light-producing organs called photophores arranged along their bodies. The velvet belly lantern shark, which lives at depths up to 2,000 meters, has photophores on its underside that create a glow. From below, this counter-illuminates the shark, making it invisible against the faint light from above. But the shark also has photophores metaphors near its eyes that shine forward, possibly to illuminate prey or communicate with other sharks. The most disturbing aspect of abyssal sharks might be their lifespan. These sharks can live for centuries. The Greenland shark, which inhabits Arctic and North Atlantic waters at depths up to 2,200 meters, is the longest-lived vertebrate on Earth. Radiocarbon dating of eye-lens proteins suggests some individuals may be over 400 years old. These sharks reach sexual maturity at around 150 years old. Imagine being a predator that lives for 4 centuries in near-freezing darkness, growing slowly, reproducing rarely, moving through a world where years might pass between meals. The biology that makes this possible is so different from surface life that these sharks represent a different approach to being alive. They're not just adapted to the deep ocean, they're fundamentally different creatures whose existence challenges basic assumptions about what vertebrate life requires. Below 6,000 meters lies the Hadal Zone, named for Hades, the underworld of Greek mythology. This is the deepest part of the ocean, found only in trenches where tectonic plates meet. The pressure here exceeds 600 atmospheres. A human body would be crushed instantly. Very few fish of any kind can survive these conditions, and sharks are rare, but they're not absent. The Mariana Trench, the deepest part of any ocean, reaches down 11,000 meters. In 2014, researchers using baited cameras photographed what appeared to be a type of snailfish at 8,143 meters, the deepest fish ever recorded. But in footage from slightly shallower depths in various trenches, sharks occasionally appear. These sharks are difficult to identify from camera footage, but they appear to be sleeper sharks or related species. What makes Hadal Zone sharks so disturbing isn't just that they exist at these impossible depths, it's that they're active, hunting predators in an environment that should be completely sterile. The pressure at these depths deforms proteins, damages cellular structures, and makes normal metabolism nearly impossible. The sharks that live here have proteins that resist pressure deformation, cell membranes with special lipid compositions, and metabolisms that function in ways we're still trying to understand. The food chain in Hadal trenches is bizarre. Most energy comes from above, as dead material sinks down, but the trenches also have chemosynthetic organisms that produce energy from chemicals seeping from the Earth's crust. Hadal sharks feed on the scavengers that feed on this material, but the entire ecosystem operates on such a thin energy budget that the sharks must extract maximum nutrition from every meal. Their digestive systems are extraordinarily efficient, breaking down nearly every component of their prey. But perhaps the most creepy aspect of Hadal sharks is how little we know about them. The deepest parts of the ocean have been visited by humans fewer times than the surface of the moon. We've spent more time and resources exploring space than exploring our own planet's deepest trenches. The sharks that live down there exist in a world we've barely glimpsed, in conditions we can barely survive with our best technology. When researchers retrieve deep-sea cameras, they sometimes find evidence of shark activity that's difficult to explain. Bite marks on bait that don't match known species, partial footage of shapes moving past the camera too quickly to identify, tracks in sediment on the trench floor that suggest something large moving through. Each of these pieces of evidence hints at sharks we haven't properly documented, species that might exist only in these deepest zones, adapted to conditions even more extreme than what we've described. Understanding why deep-sea sharks become progressively creepier requires understanding the specific challenges the deep ocean presents. Pressure is the most obvious. Every 10 meters of depth adds another atmosphere of pressure. At 1,000 meters, the pressure is 100 atmospheres, enough to crush most surface animals instantly. Sharks survive this through several adaptations. Deep-sea sharks have very soft, flexible bodies with minimal bone and lots of cartilage. Cartilage is more compressible than bone, allowing it to deform under pressure without breaking. The shark's body cavities are filled with fluids that are essentially incompressible, so the internal pressure matches the external pressure. This prevents crushing, but it also means these sharks can't survive being brought to the surface quickly. The pressure decrease causes gases dissolved in their tissues to expand, damaging organs and tissues. The darkness of the deep ocean has driven the evolution of enormous eyes in some species and the complete loss of functional eyes in others. The goblin shark has small but functional eyes, but it relies much more heavily on its electroreceptors. Other deep-sea sharks have eyes so large they dominate the skull, gathering every photon of light. Still others have eyes that are vestigial, reduced to non-functional remnants, having given up on vision entirely in favor of other senses. Temperature is another major challenge. The deep ocean is cold, typically between 2 and 4 degrees Celsius. This slows down all chemical reactions, including metabolism. Deep-sea sharks have evolved special proteins called cold-adapted enzymes that function efficiently at these low temperatures. Their muscle tissue has high concentrations of lipids that remain fluid in the cold, allowing continued movement when warm water sharks would be immobilized. Food scarcity might be the most significant challenge. In the deep ocean, there's no photosynthesis, no primary production of energy. All food must sink down from above or come from the rare chemosynthetic communities near hydrothermal vents. This means deep-sea sharks must be able to survive long periods without food, extract maximum energy from whatever they do catch, and take advantage of any food source they encounter, no matter how unusual. The evolutionary solutions to these challenges produce the creepy appearances we find so disturbing. The elongated jaws, the soft bodies, the huge eyes, the strange teeth, all of these features are responses to specific environmental pressures. But knowing why these sharks look the way they do doesn't make them less unsettling. If anything, understanding that these forms are optimized for their environment makes them more disturbing, because it means the deep ocean requires predators to look like this to survive. Despite decades of deep-sea research, we're still discovering new species of sharks regularly. In 2019, scientists described a new species of dogfish shark from depths of 1,000 meters. In 2021, a previously unknown population of 6-gill sharks was found living at unusual depths off the coast of Florida. Each discovery raises more questions than it answers. We don't know how many species of deep-sea sharks exist. Estimates range widely, from a few dozen to potentially hundreds. The difficulty of sampling the deep ocean means many species might exist that we've simply never encountered. Every new deep-sea expedition seems to find something unexpected. We don't understand deep-sea shark behavior well at all. Most of what we know comes from dead specimens caught by accident or from brief footage captured by remote cameras. We've never observed deep-sea sharks hunting, mating, or raising young in their natural environment. We don't know how they navigate the three-dimensional darkness of the deep ocean, or how they find each other to reproduce. The impact of pressure on shark biology remains poorly understood. We know deep-sea sharks have adaptations that allow them to survive crushing pressure, but we don't fully understand how these adaptations work at the cellular level. The proteins in deep-sea sharks are different from those in surface sharks, but we're still discovering new pressure adaptations regularly. Perhaps most significantly, we don't know how climate change might affect deep-sea sharks. The deep ocean is warming, slowly but measurably. This warming could affect the temperature-sensitive metabolisms of deep-sea sharks. Changes in surface ocean chemistry affect the amount and type of material that sinks to the deep ocean, potentially altering food availability for deep-sea predators. The ocean below 1,000 meters represents more than 90% of the habitable volume of our planet. It's the largest ecosystem on Earth, and sharks are among its top predators. Yet we know less about these animals than we know about the surface of Mars. The creepiness of deep-sea sharks comes not just from their appearance, but from the knowledge that they represent a world we've barely begun to understand. For every disturbing shark we've discovered, there might be a dozen more we haven't found yet, swimming in the darkness, equally strange, equally adapted, equally alien to our surface-dwelling perspective. If you found this journey into the deep ocean fascinating and unsettling, please like this video and subscribe to our channel for more explorations of the natural world's most extreme environments.